correlation and regression are similar but distinct concepts. Correlation is typically, but not always, used in descriptive studies where you're looking for an association between changes in some variable x and another variable y. And here you can see two examples of scatter plots with one with a strong positive correlation and one with a strong negative correlation. Regression, what we're looking for is, do changes in some variable predict changes in another variable? And instead of r, we're looking at r squared, and we're actually calculating in the case of linear regression, the linear equation that describes the relationship between x and y. So if you're reading a paper and it says a correlation was calculated between two variables, then you can be pretty sure, or this should at least clue you to start thinking, x is some kind of attribute variable, something we can't set, right? So it's height or weight, age. It's things that are what we can't assign them to a person. Y is also some kind of attribute variable, or it can be an outcome measure. So an attribute variable, so looking at the correlation between height and weight, age and muscle strength, those are attribute variables. We can look at outcome measures as well. So if we're looking at age and muscle strength from an intervention standpoint, we might want to know, did the ending muscle strength, was that correlated to the age of the participants? Did older participants end up with less muscle strength than younger participants? What the authors are also telling you is they think the values of x and y are related, and they want to know how strong that relationship is, but they aren't trying to show a causal relationship, that a change in x causes a change in y. In regression, x is some sort of active variable, something you can typically change, like duration of an intervention or dosage, and y is an outcome measure. And what the authors think is they can predict the value of y based on the value of x. So if you tell them the dosage or the intervention or the duration of an intervention that somebody gets, they can predict what their outcome would be. But they're still not showing a causal relationship. So here's some of the symbols and concepts that we'll be talking about. So in correlation, the thing we're most interested in is this correlation coefficient R, and it's telling us how linear is the relationship, how close to a line does the scatter plot fall. And when you get a p-value for correlation, you're measuring what's the probability that R is actually zero, that there is no linear relationship. And when we get a confidence interval around R, there we're looking at, could R be zero? So can we rule out the possibility that there is no linear relationship? Regression, this R squared is this R squared. So the regression coefficient is the square of R. And we're using it to measure how accurate our prediction is. And we don't test it with a p-value or a confidence interval. So R squared, we're not doing any sort of further statistical analysis on. What we are doing statistical analysis on is what you'll see as either B or beta. That's the slope of the regression line. So that's this here. So when you do regression, you get an R squared. You also get the equation for your line, which is intercept plus slope times x. And what that B or beta is telling you is how big a change in your outcome do you get from changing 1 unit of your input, of your predictor variable. Your p-value is looking at what's the probability that B is actually 0, so that your line, what's the probability that your line is actually flat and that you don't get any change in your outcome variable when you change your predictor variable. And your confidence interval around B or beta is looking at, can we rule out the possibility that beta is 0 with 95% certainty.